Okay, section 3.7, video 2, we're on to example 3 with optimization. Again, the rest of these are just going to be examples. So example 3 says a page needs to contain 24 inches squared of print. The margins at the top and the bottom are 1.5 inches. The side margins are 1 inch. What dimensions of the page will use the least paper? Okay, so if that didn't all make sense to you right off the bat, it's okay, read it again. So it says a page needs to contain 24 inches squared of print. So that's an area because it's something squared. So I'm going to sketch a page, and that's where the printed area is. So we know that this area right here has to have 24 inches squared of print. So this is like where the print is of the page. The margins at the top and the bottom are 1.5 inches. So margins are not printed on, so that's going to be a space outside. It says the margins at the top and the bottom are 1.5 inches. So that space is 1.5. That space is 1.5. Side margins are going to be 1 inch. So that space right there is 1 inch. This space right here is 1 inch. What dimensions of the page will use the least paper? So least paper, we're trying to minimize something. So what we need to come up with is we need to come up with a primary and secondary equation. Well, it looks like the secondary equation is actually going to be the easiest one to do. If we were to call this piece right here, I tend to, oops, did not mean to erase that. If we call that piece the width, and then we call this piece right here the length, because I tend to call the longer part the length, then the width times the length is going to equal 24 square inches, because we know the length times the width of a rectangle is the area. So we'll have the length times the width equals the 24 square inches. Well, that's good. I can solve that for either L or W. Well, now I need to come up with a primary equation, which is for the entire page. So it looks to me like the entire page is going to be this whole thing right here, which is the length of the blue piece plus an additional 1.5 on top and 1.5 on the bottom. So really it's going to be the length plus 3 more inches total. So I know I'm going to have the length plus 3. That's going to give me the whole length of the green page. Then the width, it's going to go that direction, which is going to be the width of the blue part plus another, it looks like 2 inches, one from either side of the margin. So we're going to have the width plus 2, and that's going to equal the area of the entire piece of paper. So now I can reduce the primary equation, which is the top one, down to one variable, and it doesn't really make any difference which one we pick here. We could solve for L or we could solve for W. I'm going to choose to solve for L, but it doesn't really matter. So if I solve this for L, I can divide both sides by W, which gives us 24 divided by W. So that means I'm going to take that information and I'm going to plug L, 24 over W, in for the L in the primary. So we're going to get that A equals 24 over, oops, not over 3, over W plus 3 times W plus 2. Okay, now I've got a primary equation which is down into terms of one variable. I'm going to go ahead and multiply this thing out. I'm going to FOIL it just to make it a little bit easier to take a derivative as opposed to using a product rule. So let's see, first times first is going to be 24 over W times W. The W's will cancel out, give me 24. Outside is going to give me 24 over W times 2, so that's 48 over W. Inside will just be 3W, and last will be 6. Okay, so I'm going to go ahead and rewrite this. I can combine the 24 and the 6, although it doesn't really matter because those are going to go away with a derivative. I'm going to write that as 48W to the negative 1, again, just to make it easier to take a derivative. So now let's do A prime. Derivative of 30 is gone. Bring the negative 1 out front and multiply it. We get negative 48W to the negative 2 plus 3. Need to set that equal to 0 to find the critical values because we are trying to minimize this one. So let's add the 48w to the negative 2 to the right. And remember, w to the negative 2 means it's really over w squared. So we're going to add that over, and we're going to get 48 over w squared. Multiplying both sides by w squared gives me 3w squared equals 48. Dividing by 3 gives me that w squared equals 16. And then taking the square root, w would equal technically the plus or minus 4. But in this case, I only need the positive 4 because we are talking about the width of a piece of paper. So it can't be negative. In this case, I think that taking the second derivative is going to be the easiest test. So if I take a double prime, I'm going to do it from here. Let's see, bring the negative 2 out to the front, multiply, and you're going to get 96 w to the negative 3, and the derivative of 3 is 0. So if we rewrite that, that's the same thing as 96 over w cubed. So I need to test my critical value, which is 4, in the second derivative. So if I plug 4 in there, I'm going to get 96 over 4 cubed, which is 64. Well, that's a positive value. I didn't really need to know that it was 64. I just need to know that it was positive. This is positive, which indicates that the concavity is up. Okay, I'm sure you probably heard that phone ringing in the background. Sorry about that. I had to pause this for a second. So anyway, we were to the point where the positive second derivative meant that the function is concave up, which of course then indicates that we have a minimum. So we have found the location of the minimum with our width, which is 4, which means we need to find the length. So if the width is 4, then to get the 24 square inches of print, the length would be 6. But that's not the width and the length of the entire page. That's just the printed area. This wants us to actually figure out the minimum size of the page. So we have to remember that the original equation for the primary came from right here. So really, I'm going to take the length and I'm going to plug it in there and add 3 to it. So that means that my actual length is going to be 9, and my width was adding 2 to it. So that means 4 plus 2 is 6. So it looks like I'm going to have a 9 by 6 square inch page that will minimize the size of the page. So hopefully you can see how this would actually be a very practical example in real life. Publisher is probably going to want to know, okay, if I need to fit this much print on my page, what's the smallest amount of page that I can have to make this fit? Because, you know, I'm trying to save paper, I'm trying to save money. So for them, it would be cost effective. All right, let's do another one. Find the minimum distance. So we want to minimize distance here. And it says, which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? All right, so it probably would help to at least have somewhat of an idea what we're looking at here. So the graph of y equals 4 minus x squared, that is a parabola which opens down, and it's got a y-intercept of 4. So it's going to look something like this. And the point 0, 2 is right here. So it says we want to minimize the distance. So you might think that the distance straight up to the top might be the minimum distance, but maybe it's not. Maybe it's someplace over here. Well, that doesn't make sense. You can kind of clearly see that that's a longer distance than it is to the top, even as bad as I've probably drawn this. But maybe it's someplace else. So we want to minimize the distance. Well, in order to do that, we're going to need the distance formula. Okay, and if we don't remember what the distance formula is, remember that it really is based off the Pythagorean theorem. And it's going to be the change of the x's, so x2 minus x1 squared, plus the change of the y's, y2 minus y1 squared. And then we take the square root, because really if we squared both sides, you would get the change of the x's squared plus the change of the y's squared equals the distance squared. So it really comes from a triangle. It comes from Pythagorean theorem. The secondary equation is the one that's given to us. Y equals 4 minus x squared. It tells us equals 4 minus x squared, tells us that's a secondary equation. Okay, so let's go ahead and set up our distance formula with the primary reduced with the secondary. So we have the distance is going to be x2 minus x1 squared, but x1 in this case is 0. So it's really going to be x minus 0 squared. I don't need the sub 2 anymore since I'm plugging in the other value. For y, the y1 value is 2 because that's the actual point. So y2 in this case is just going to be the 4 minus x squared. So we're going to have 4 minus x squared minus 2 squared. Let's go ahead and reduce this. So x minus 0 is just x, so that's x squared. In the second parentheses, we get 4, and we got a minus 2, so that's going to be a 2 minus x squared squared. Let's go ahead and FOIL that thing there out. And we're going to get x squared here, and then we're going to get, let's see, that's going to be 4 minus 4x squared plus x to the 4th. So combining whatever like terms and just kind of reorganizing this, we're going to get x to the 4th. I'm going to have a negative 3x squared when I combine those x squared terms, and then plus 4. So here's the really cool thing. I don't have to use the entire square root because minimizing or maximizing the distance is the same thing as minimizing or maximizing the function that's under the square root. So really all I have to do is minimize or maximize that particular function. And that's because it's all relative. If I include the square root, it's going to give me a different derivative when I end up with a derivative, but it's going to end up at exactly the same point. So really I don't have to deal with the square root. That's really actually very nice. So I'm just going to take f of x to be the function that's underneath the square root, so I don't have to deal with that whole chain with the square root and everything like that. That just becomes more of a pain. So let's go ahead and max or minimize this function. So f prime is going to be 4x cubed minus 6x. Okay, I want to set that equal to 0. I can factor out 2x, which is going to leave 2x squared minus 3. So let's see, splitting this up, we're going to get that 2x equals 0 or 2x squared minus 3 equals 0. So either x is 0, or let's see, adding 3 and then dividing by 2, we get that x squared is 3 halves. So taking the square root of that, x is the positive or negative square root of 3 halves. That is not a pretty number right there. So let's go ahead and figure out which one of these things might give us a minimum. So the easiest thing to me in this case would be to do the second derivative test. I don't want to do the number line with those awful values if I don't have to. I could, but I don't want to. So I'm going to do the second derivative because this is an easy second derivative to do. I'm going to take it from this one. So the second derivative is going to be 12x squared minus 6. So let's test them. If I were to plug in my first critical value, which is 0, I'm going to end up with negative 6. Well, that's a negative value, which means that it's concave down there, which means that that is a maximum. I'm not looking for a maximum, I'm looking for a minimum. So let's do the second derivative evaluated and in this case, it's not going to matter if I plug in the plus or the minus of this square root since I'm squaring it. If I plug that in, I'm going to get 12 times square root of 3 halves squared is 3 halves minus 6. 12 times 3 halves is 36 over 2, which is 18 minus 6. So that's positive, which means that it is concave up, which means that that indeed gives us a minimum. So what does the actual question ask? Since we have now found the x value, it says which points on the graph are closest to 0, 2. So this is giving me the x values, okay, the square root of 3 over 2 and negative square root of 3 over 2. So we just need to find the actual points. So I'm going to plug positive and negative root 3 over 2 back into this equation right here. So we're going to get 4 minus those square roots to find the y values. So 4 minus plus or minus root 3 over 2 squared. Again, root 3 over 2 squared is 3 halves. So 4 minus 3 halves. In terms of halves, 4 is 8 halves. So 8 minus 3 is 5 halves. So it's going to give you 5 halves. So our points are the positive root 3 over 2, 5 halves, and the negative root 3 over 2, 5 halves, which if you kind of go back up to your graph, like I said before, is definitely not straight up. Positive root 3 over 2, 5 halves, I don't know, it could be right here, maybe in right here. So according to this, these are the shortest distances. Going straight up is actually not as short as going off to those right-hand point and left-hand points. So that's the shortest distance. So we have found the 2 points which minimize that distance. All right, let's do one more. Okay, we've got an open box with a rectangular face that's to be constructed from a rectangular piece of cardboard 16 inches by 21 inches by cutting a square from each corner and folding up the sides. Find the size of the corner square, which will maximize the volume. A lot going on there. So we have an open box. Think of it as like a tissue box, but without the top. So we have an open box with a rectangular face, which is to be constructed from a rectangular piece of cardboard. Well, I can draw a rectangle. That's not too difficult. There's my rectangular piece of cardboard. It says it's 16 by 21, so we'll call that 16. We'll call that 21. We are going to cut a square from each corner and then fold up the sides. Okay, so see where we're going with this. We're going to cut a square out of each corner, and then we're going to fold up the sides. So the one thing we don't know is we don't know the size of the square, because that's actually what we're trying to find here. We're trying to find the size of each corner square, which will maximize the volume. So since I don't know the size of the square, the only thing I do know about a square is that the sides are all the same. So I'm going to call this side X, which of course makes that side X, makes all 4 sides X. But my cuts are all going to be X's. I could call it whatever I want to, just made more sense for me to use X. So let's see our primary equation. We want to maximize the volume. So I need the volume of a rectangular prism because it's going to be 3-dimensional. So I need the volume of a rectangular prism, which is length times width times height. I need a secondary equation. In this case, I think we're going to have multiple secondary equations because I have a way to define the length, the width, and the height all in terms of one variable X. So let's look at this. The length is all of this side right here, but I'm cutting off an X distance here and here. So it's really going to be the whole 21, but I'm going to take away 2 X's. So my length is going to be 21 minus 2X. Likewise, the width, which is going to go this direction, is going to be the entire 16, but again, I'm cutting off 2 X's. So it's going to be, the width is going to be 16 minus 2X. And when I fold this thing up, you have to visualize this a little bit. When I fold this thing up, the height of this thing is really just going to be this X. Okay, when it's folded up, that's the height. So the height is just the length of X. So now I can replace the length, the width, and the height with all 3 of those equations and put everything in terms of X. So my new volume equation is going to be length 21 minus 2X times width 16 minus 2X times height, which is X.